on the bearing capacity of foundation, how to design foundation. Today we are going to look at some of the calculation aspects, then we will also continue from there. A strip foundation of width D gradually compresses the foundation soil underneath due to the vertical load from superstructure. So we're saying that let QF be the final load at which the foundation soil experiences failure due to the mobilization of plastic equilibrium. The foundation soil fails along the composite failure surface, and the region is divided into 5 zones. The zone 1, which is plastic, the zone 2, numbers of zones, which the 2 numbers of zone 2, which are the zones of radial shear, and 2 zones of zone 3, which are the zones of linear shear. Considering the horizontal forces, we talked about all these equations the other day, and this one is just a glance through what we did the other day. And we were also coming to the general bearing capacity equation. So after the development of design bearing capacity equation, several investigators worked in this area and really find the solution. That is the Neyhoff 1961, the Lundgren and Motsin 1953, Bella 1952. All these were the researchers and investigators with the comprehensive work to find the fault that has to do with the desired bearing capacity equation. With the desired bearing capacity equation, it was presupposed that it has the shortcomings. So some investigators came up with some idea and decided to work to improve on that desired equation. However, other investigators such as Brent Hansen 1960, 70, Lissig 1973, 63 conducted several laboratory investigations and improved upon the desired bearing capacity equation in design of footing of structures. Different solutions shows that the bearing capacity factors N and N do not change much. As we said, however, for a given value which is less than 75th value of N obtained by different investigators varying widely. This difference is because of the variation of the assumption of the wedge shape of soil located directly below the footing, as explained in the following paragraph. While deriving a bearing capacity equation for a strip footing, Zadi used the case of a rough footing and assumed that the sizes AJ and BJ of the soil wedge ABD would make an angle phi with the horizontal. Later model test, for example, that the B and this is also 1958 shows that Zadi assumption of the general nature of the rupture surface in soil for bearing capacity is correct. And however test shown that the sizes AJ and this thing we all talk about it came to what we mean. We also came to what Brent Hansen bearing capacity. Let's come to Brent Hansen bearing capacity equation. Brent Hansen 1970 also proposed a general equation that allow us to determine the bearing capacity of footings of any shape and size and in any inclination of loading or the bearing surface. Brent Hansen's equation are often used for footings on slope. As mentioned, Brent Hansen equation was normally designed for foundation that is to be constructed on slope. The equation works widely. He designed a foundation that are to be used on slope. As mentioned in the previous section, bearing capacity depends on many factors. Zadi's bearing capacity equation does not take into consideration all the factors. Brent Hansen and several other researchers have proved and provided a comprehensive equation for the determination of bearing capacity called generalized bearing capacity equation, considering almost all the factors mentioned above. The equation for ordinary bearing capacity is as follows from the comprehensive theory, where we have the general bearing capacity equation illustrated over there. Here we have the bearing capacity equation factors given by the expressions which depends on phi. They are all has been explained. Equivalent available for shape factors. We have shape factors SC, SQ, Q1, SR, depend. These factors also depend much. Depth factors where we have DC, DQ, and D lambda, and load inclination factors, IC, IQ, and I lambda. These are the factors that has to be done with the bearing capacity equation. So it is what we based on the other day and to determine the kind of foundations that we need to construct and to design. So these are all investigators who did very well when it comes to designing of foundation. They took Tizagi's bearing capacity equation and they improved on that. They all did very well in doing that. Tizagi later on, they all helped in improving upon the theory of Tizagi. The effects Vixit's 1963 conducted several laboratory load bearing tests and circular and rectangular plates supported by sun at various relative densities of compression. Variation of and obtained from those tests, where D is the diameter of a circular plate or width of a rectangular plate, and it's a dry unit width of sand, as shown in Fig 3.2. It is important to note that from this figure that for about 70% of general share type of failure in soil occurs. On the basis of experimental results, Vixit's 1973 proposed a relationship for the model of bearing capacity failure of foundation resting on science of these factors is to reduce the bearing capacity of the soil. So if you look at it, we have the sand here, circular foundation, and we have the deep foundation. The effects of shape of foundation. The shape of footing influences the bearing capacity. Zagi and other contributors have suggested the corrections to the bearing capacity equation for shape and other strip footings based on their experimental findings. Following are the corrections that for circular, square, and rectangular footings. So Tizagi and the other contributors came together and realized that no, the first formulas and the first empirical equations that they proposed to the lab to do an extensive research and also to improve on the equations that model to come up with equations that could solve the problem of circular footing, square foot. The bearing capacity equation is given at 1.3 Cn. Square footing will also be given as Qn equals 1.3 Cn plus lambda . And all this equation. Then we have to also come to the effects of water table fluctuations. The basic theory of bearing capacity is derived by assuming the water table to be at greater depth below and not interfering with the foundation. It should be below, and then the water table should not interfere with the foundation. The depth of the water table to where the foundation should be measured. However, the presence of water table at foundation depth affects the strength of the soil. That's what it's saying. When the depth of the foundation table, the depth of the water table, when it's closer to the foundation, it affects the strength of the soil. It affects the strength of the soil. Further, the unit of soil to be considered in the presence of water table is submerged density and not dry density. Then we say hence the reduction coefficient RW1 and RW2 are in second and third terms of bearing capacity equation to consider the effect of water table.